Hello, hello, chemistry. Okay, uh, these are the polyatomic naming rules that the chemistry classes took notes over on Wednesday. I'm not going to spend as much time on these in this video because you guys can just pause it and copy them down. I am going to talk real quick over some of the more important points. Specifically, ides are usually your most common ion. So, for example, phosphide. This is the point where I'm missing a marker. Phosphide is P-3. And if we look at periodic table, phosphorus is right here. So this is group 18, 17, 16, 15. So 5 valence electrons means its most common ion is going to be -3. Or if you forgot, 0, -1, -2, -3. For the non-metals. The metals don't work quite the same, but you don't have to worry about that. All right. So phosphide is simply the most common ion of phosphorus. Okay, and that is the case for most of our ides. Now, there are a couple of exceptions to that, like hydroxide and cyanide and amide. They are not the most common ion. They're actually real polyatomics. Poly meaning many, atomic meaning atom. This is not really a polyatomic. This is just an ion. But it's an extremely common ion that you need to know the name of. So I included it in this set. So cyanide, Cn, -1. Hydroxide, OH, -1. And amide, NH2, -1. are the three simplest polyatomics that you're going to be working with. With the exception of hydroxide, they do not have any oxygen in them because it's not actually a polyatomic for most of them. They're just simple ions. The farther down we go, these other 4 that we're going to discuss are actually for polyatomics. Now, there are exceptions for them, but we'll talk about those as we get there. So I'm going to step off screen real quick. I'm going to let you copy this all down. I'll scroll down so you can get 8s, and then I'll put some more information on the screen for you. Oh, if you're looking, there is no spot in your actual notes for this. You'll have to create a new doc or add it to the notes that you've already got. So this is not something that's actually got a spot in your notes already. Now, something I do need to point out is that ide, ite, and ate are all suffixes. They all go at the end of a word. But per and hypo are prefixes, and they come at the beginning of a word. So bear in mind that you might have per and ate in the same word. In fact, you have to, almost. Ditto for hypo. Hypo and ite, almost always in the same word. Now, just because you have just because you have an ite, doesn't mean it has to include hypo. But if it has hypo, it probably includes ite. So I'll step off again. Give you a second to pause this and get the rest of these. And then I'm going to scroll down and show you some of what these actually mean. Okay. This is using the information that you just copied down. So for some given element, like chlorine, there is a root, in this case, chlor. So they all follow the same pattern of per root 8. So per chlor 8. And those are going to have the formula of the symbol O4, and then whatever the charge is going to be based on what the element is. So usually that's going to be based on its most common ion. So since chlorine has a -1 charge, all of these are -1. So root 8 is O3, chlor 8 is ClO3, root 8 is root O2, chlorite ClO2. Now, there are a couple of exceptions to this trend. None of them are the halogens. So fluorine, chlorine, bromine, and iodine all follow this pattern. Okay, nitrate and nitrite, they tend to follow this pattern. There's no per and there's no hypo. But the nitride ion is slightly different from nitrate and nitrite. So for nitrogen, make sure I'm standing off screen, nitride is a -3, but nitrite is NO2 -1. Ditto for nitrate. It's a -1 instead of a -3. So this is one of those that is just slightly different. You'll have to pay attention to. Now, I'm going to point out something on the periodic tables that I gave you. So you have a digital version of this in Classroom that you can pull up. Okay, this, if you flip it over on the back, there's a polyatomic ion list here. And at the bottom is the information from the board. And at the bottom of that, it includes the exceptions. Okay, now this is the key. Sulfur, phosphorus, and chromium are the exceptions to this rule, or to this pattern. It's not really a rule, it's more of a pattern. Their 8s are all O4 instead of O3. So I'm going to erase nitrogen here. So sulfur, well, yeah, okay, is S -2. Can you see that? Yeah, you can see that. Okay. Its 8 is SO4 -2 instead of SO3. Phosphorus and chromium are the same way. So after that, though, the pattern holds. It's -1 as you move down. So SO3 for, it's not a 2, for sulfite, and SO2 for hyposulfite. And the charge is the same in all of these. The same is true for phosphorus. Now, chromium, you only need chromate. It's the only one on your list that you actually have to know. So you don't have to worry about the pattern for anything else, but chromate is CrO4 -2 instead of CrO3 -2. Remember when I told you during our general or lab safety rules to make sure you looked real close at the formulas, because there's a lot of really similar ones? This is why. Okay, this naming system is very specific and it gives us the information we need, but if you're not paying attention, it's real easy to make a big mistake. So that's another reason why I want you to learn these. So copy this down if you think this will be helpful to you. This is going to be up here for another second or two, and then I'm going to put up some more prefixes and give you some more examples. All right. The first one of these four that I want to go through is the simplest, and that is die. Die just means two. And of course, in true fashion, it's just like you're in class. I didn't have my highlighter turned on. Die just means two. So whenever you're going through, if you see die in anything, it's just telling you two. So a really good example of this is going to be chromate, because you don't have chromite, perchromate, and hypochromite. You just have chromate and dichromate. So chromate, make sure I'll do it down here, is CrO4 negative 2. And that's going to be chromate. Dichromate the obvious is Cr2, because that's what the dye tells us. But the oxygen, unfortunately, doesn't quite follow the same rule, which is a little annoying. It's O7, but the same charge. So dichromate is one of those slightly odd ones you're going to have to pay attention to. Next is bi. Now, bi just means add hydrogen. Okay, now this is the only one. This is the only prefix that you have to know that is going to possibly change the charge of an ion. Okay, all the rest of the roots have the same charge. If it has phosphorus as the root, then it's -3, no matter what, unless it's bi. If it says bi, then it changes the charge to -1. What's the charge of hydrogen? Well, hydrogen has a charge of +1. So let's look at a couple formulas. Sulfate is SO4 -2. So bisulfate is going to add hydrogen to this until the charge becomes -1. Well, it only takes one hydrogen to increase this to -1. Hydrogen is always drawn first, except for in ammonium and amide, because it's acting as an anion there, which is a whole other conversation. Don't worry about that. So HSO4 -1 is bisulfide. Now, what about phosphate? It has a charge of -3. So biphosphate, we add hydrogens to this until the charge becomes -1. Well, in this case, it's going to take 2 hydrogens instead of just 1. So H2PO4 -3. Nope, not -3, -1. And that's pretty well it for bi. The next one that can be annoying and somewhat confusing is thio. Because thio changes your formula a little more significantly than any of the other ones that we've worked with. So I'm going to start with cyanate. So we have cyanide and cyanate. Notice that cyanate just has one more oxygen than cyanide. Now, to turn cyanate, I'm going to write this down, into thiocyanate, we have to remove one oxygen, so we would lose the oxygen, and replace it with a sulfur. So it's SCN instead of OCN. For most of these, it's pretty simple to make that distinction. However, sulfate and sulfite can be extremely confusing. So I want to go through one of them. So let's do sulfate. Now let's do sulfite. I'm going to do sulfite. Okay, this is a sulfite ion. To turn this into thiosulfate, we have to remove an oxygen, so it becomes O2, and we replace it with a sulfur. So we already have a sulfur, though, so it's going to become S2O2 with a still -2 charge. Okay, this is one of the more annoying ones. This is one of the ones that can get confusing because it changes the formula more significantly than a lot of the others do. The last one is pretty straightforward. It really only affects one for you guys, and that is ium. Ammonium has a charge of +1. Okay, ammonium is one of the oddballs. There's a few oddballs I'm going to put up on the screen here to try to point them out, but they're all a little weird. They're just kind of outliers. They're common ones that you need to know, but because they're so common, they all have common names that don't follow our naming rules. But you have to know them because they're going to pop up a lot. The most annoying is the one I'm going to do first, and that is oxalate. Okay, oxalate, I don't know where this name came from. I have no idea who thought that this name made sense. But this is the name that we have, and it's the one that we need to know. So, C2O4 -2 is oxalate. Another one that's a little bit odd, well, we already talked about dichromate. Ammonium. Ammonium has nitrogen and hydrogen in it. It is NH4 +1. And I need to put more space between the next two. So ammonium is another one that's a little odd, and I'm blanking. What's some of the other odd ones that you guys need to know? Permanganate follows the rule. We already talked about cyanide. Acetate and formate. I knew there were two more. Now, these actually have two formulas. They have an organic formula because they are organic ions, and they have an inorganic formula. You can give me either when we're quizzing over these, but you have to be able to recognize both too. Now, you're most likely to see the organic, or the inorganic. I can't talk. Most likely to see the inorganic formula, not the organic formula. So if you are just absolutely committed to only learning one of them, learn the inorganic, because that's the one that you're most likely to see. So, of course, I'm going to start with the organic formula, so that you actually see both of them. These are the organic formulas. Chuku and Huku, as some of my students like to refer to them. They are written in a way that makes sense if you know organic chemistry. But since we aren't doing organic chemistry, they're really kind of weird for us. But I want you to see them because you might see them again, and I want you to go, oh, I know what that is. I'll be right back. Need another marker. All right, now the inorganic. Okay, the inorganic way to do this is just HCO. So we have, CHO. C2H3O2 -1 and CHO2 -1. So these formulas are the same compound or the same molecule, polyatomic, that's what I'm looking for, the same polyatomic ion, but they can be written in a couple of different ways. I am absolutely fine if you only learn the inorganic formula. I might make it a bonus question to know the organic formula. So it might behoove you to learn Chuku and Huku, but CHO is the one you absolutely have to know. This one in particular, acetate, will show up a lot in Unit 3. So you need to know that formula. By the way, if you are one of the people who is thinking, oh, this is just one of those things that's passing, if I don't learn it, I'll be fine, that is not the case. If you do not learn these polyatomic ions, you will fail Unit 3. You must be able to identify these in order to do Unit 3. So you have got to spend some time on them. That's why I'm making it such a big deal to be focusing on these. Why we spent an entire class period talking about how to learn these and giving you guys tips. So take the time, learn them. It will save you a lot of headache later. Okay? Polyatomic ions, that's all I have. I will step off screen so that you guys can get one last look at everything, and then that will be the end of the video. So have a wonderful night, and I will see you all next time.